Okay, shall we begin? So first, just a few announcements. If you are following along in the text, but this is kind of a, is that an echo? It's just very loud in here. Oh, okay. If you are following along in the textbook, chapter 3 is on lenses, although we will go into it in more depth than London does. And then there is this additional optional reading, but it's in the course reader, which, as I said before, because of copyright reasons, I can't hand out here at Google. But it's a standard textbook on optics. And the course schedule says what part of it I'll be reading, covering. Your assignment this week, if you're doing the assignments, and a number of people are, is sports and action. So in the weekly rhythm of the course, that'll be due this Sunday night. And then if you did submit an assignment for assignment number 1, which was bad photos, please do the peer-to-peer commenting, as I said in the group emailing list. And if you're using the Dory today, I've broken it into topics, and today is March 28th. So I'll be watching the March 28th topics of the Dory. Okay, so today we're going to talk about lenses. And I'll just start by trying to motivate why it's for a photographer to study what goes on inside lenses. And we'll talk about the thin lens approximation. We'll do both graphical and algebraic formula, but I'll concentrate mostly on the graphical constructions. We'll talk about thin versus thick lenses, and I'll tell you some interesting properties of lenses as they relate to photography. We'll talk about depth of field, and I'll give the formula that I did as a teaser at the beginning of the course. Then we'll eventually, probably, this is on Thursday, this is maybe as far as we'll get today, talk about aberrations and things that go wrong with lenses. And there are lots of them, and they affect photography. And then we'll talk about the designs of telephoto and zoom, some special lenses. Okay, so cameras and their lenses. So I've already shown something like this, and there's a bunch of glass there. The digital point and shoot has a smaller section of glass, but it also, of course, has the same thing. In some point and shoots is a mirror that bends it down, so most of the glass is actually down vertically in the body. Some cell phones used to do that. I don't know if there are any commercially available that do that now. I love these cutaways of lenses. It's actually not as easy to make a cutaway like this as you think. You have to carefully cement things in place as you run the saw. But I just love looking at these. You see these at trade shows every once in a while. And the aperture's most likely right in there, in this lens. So why is it important to study lens quality? So lens quality varies, and it affects your photograph. So the toy at the top is $1,700, a 70 to 200 f2.8 zoom. This is almost the same range, but it's much lower price. And why is the one at the top so bloody complicated? I count 23 pieces of glass here. That's that's a lot. What's it doing in there? So here's a picture that I took of the big dish at Stanford, and I took it first with this set up here. So the body is not that important. It's micro four thirds, but it's got this very nice Leica 90mm lens on it. And there's a blow up of the top of the radio telescope. I then took the same picture with essentially the same body, but with a sort of a kit lens that's 45 to 200, and got that picture. So there are a lot of differences that you can see there. Looks like I'm carrying about the same weight of stuff around with me, but I get a rather different picture. So first of all, this is a prime lens, meaning fixed focal length, and this is a zoom lens. And the difference in optics between them accounts for some of the difference in quality. You can see the contrast is higher. You can see the sharpness is higher. So contrast, just the black-white range. It's also a huge difference in price. And so there's probably a difference in the quality of the optics and even the mechanics. And it turns out that the mechanics are actually important in lens quality. A Zeiss engineer told me once that they actually spend more money per lens that they ship on the mechanics than they do on the glass itself. Because if it, for example, if two pieces of glass are not perfectly centered, then you'll actually get aberrations. And so it's important that the mechanics be good as well. So here's another example. And in this case, I used the 100 to 400, that's this lens here, sometimes called the dust pump, because it pumps dust into your sensor as you use it. It's a zoom lens from 100 to 400 millimeter focal length. Or this one, which I brought in last time, but I didn't want to carry it again. It's the prime, the 300 2.8 prime. Okay, so what's different between them? Obviously, again, a huge difference in price. And this is a prime, and this is a zoom. So in this case, the optics is probably roughly the same quality. They're both Canon L series lenses with the little red line, but one's a prime and one's a zoom. And this is also a little bit more glass because it's a lower F number, and that accounts for some of the differences in price as well. And if you have to look a little bit more closely here, but you can see that this is a bit sharper than this. You can see chromatic aberration. You see the kind of colored fringes at the edge. It's kind of orangey on the side here, which isn't actually true in the scene as captured by the better lens. So there is some difference in sharpness and the aberration. It's a little bit softer over here. Okay, so let's study that. And we're going to start all the way back with Christian Huygens and his principle of traveling waves. So light could be modeled as a set of traveling waves. So he actually first published this before Newton published his corpuscular theory of light. And you can either represent it as these waves, or you can represent it as the perpendiculars to the waves, which are rays. And so that's the perpendiculars, if taken by themselves, are the basis for thinking about geometrical optics. So diffraction causes these to bend at a slit. And so what happens at a small slit is the following. You have these waves, and I'll show them diagrammatically like this, and they're moving in this direction. So you can think about that as being the peak of a wave, if you'd like, sort of like that. And it reaches a narrow slit. And what happens is the waves begin to move out like that. And so some of them, of course, blocked. And I'm drawing both the perpendicular and the waves. Now, if the wavelength is small relative to the slit, or I can draw that very simply as a big slit, like this, then there's kind of a section in the middle that bends very little or not at all. And maybe there's a little bit of bending at the edges. And so if the slit is small, this is the regime of wave optics, or sometimes called physical optics. And if the slit is large or the wavelength is small, then this is the regime of geometrical optics. And so I say that here. As lambda, the wavelength, goes to 0, or the slit gets big relative to that, there's less diffraction, and rays are straight, or so-called rectilinear propagation. So we will start today by considering only geometrical optics, and then we'll reintroduce wave optics and the diffraction effects that it creates on Wednesday. Okay, so Snell's law of refraction is what governs what happens at an interface. So I'm not going to be drawing all day today, but there are just a couple of drawings that it's helpful to actually kind of draw as you go. So what happens when light reaches an interface where the density of the material changes? The density of material causes the speed of light to be slightly different. So what happens? We have a wave coming in like this. So this is, again, the peak of the wave. And we can think of this distance here as being the velocity of light in this medium times some amount of time. And that gives that distance there. Okay? So what happens when it reaches a change in density? So let's call this the boundary between two different density materials that have different speeds of light. So one thing you could say is, well, let's see, so if it's denser and therefore slower, well, then so these peaks must be closer together. So maybe they're like that. But if you work that out, well, that doesn't actually work. Because, you know, where does this extra peak come from here? I mean, that's actually an impossible diagram. You can't do that, because you would have to generate a peak in the middle of nowhere. So what actually happens in order that the peaks remain continuous is they have to bend like this. And so that this distance now becomes V2 delta t. Now the peaks are still connected. So that's what actually happens. Ocean waves slow down as they reach the shore. In shallower water, they travel slower. And so they bend as well. And that's why the waves seem to come in roughly perpendicular to the beach all the time. They may or may not be perpendicular out in the open ocean, but then they bend to be parallel to the beach as they come in. And so that, whoops, did we lose something here? Oh boy, new Google software is available. No, no, definitely not. Let's try that again. So we can draw this relationship using the perpendiculars rather than the waves. And then we get that relationship up there where the perpendicular bends toward the normal, which is the vertical line. And this distance over this distance, which is that ratio here, is as the sines of the angle. And you can work that out just from the geometry of what I just said, those constraints, that the peaks have to stay connected. You don't need to know anything else. Which goes as the ratio of the velocities. Now, instead of actually representing them as velocities, it's common to use these indices of refraction, which are themselves ratios of velocities. But it is the same effect. And so the index of refraction is defined as the speed of light in a vacuum over the speed of light in some medium. And if these are two separate mediums above and below, then they'll have different indices of refraction. Okay, so what are some common indices of refraction? Whoops, some common indices of refraction. Air is almost 1. It's not exactly 1. It's 1.0003 in room temperature, but will become slightly denser or less dense in hot or cold air, and that's, of course, what gives rise to mirages. So a hot pocket right near the ground will make the light of the sky do this and come to your eye. And so you're actually looking at a part of the sky, and that's what's causing a mirage. And you can kind of see that. That's a bit of the sky. That's actually a bit of the mountain reflected. And that's because the density changes. So it goes roughly with the density, but it is not linearly proportional. The index of refraction is not linearly proportional to the density. So water is 1.33. Glass is somewhere in the range 1.5 to 1.8, depending on the impurities that are put in it on purpose in order to make photographic lenses. Okay, so in a glass lens, the light typically bends twice, once as it enters the glass and one as it exits. And so it's just two applications of the rule I just gave you. The first time it bends toward the normal, meaning to bring it closer in alignment with the perpendicular at that point on the lens. And then as it's leaving, going from a more dense to a less dense material, it bends, here's the normal here, to that part of the glass. It bends away from the normal as it goes to a less dense material. And so it seems to bend twice in the same direction, but it's for two different, for the opposite reasons. And then light traveling perpendicularly, which would be down here, does not bend at all. Okay, so what shape should a refractive index be in order to make parallel rays come to a point? Someone want to yell out an answer? What shape should that interface be to bring parallel rays to a point? edge of a circle. Convex, what shape convex? So I hear someone saying spherical, essentially, if it were 3 dimensions.
On each side, but you have to put 2 together, otherwise it would be too big in the middle.
Uh-huh. So actually, that doesn't create a focus. Surprisingly, it needs to be a hyperbola. So you know that a parabola will take light and focus it at a point, but if you want to focus it not inside the shape, but beyond it, it's a hyperbola. It's a conic section with a focus on the other side of the section. So if you put 2 of those together, you'll make a lens. And that lens will perfectly focus light from here to here. And you can go to Edmund's catalog and you can buy hyperpoloid lenses. They'll be perfect, but they're really hard to make. And they only will fix some of the aberrations. We'll come back and talk about that later. Turns out that since time immemorial, spherical lenses have been much easier to make. Because all you have to do is you have to take something very hard and glass which is a bit softer and do this kind of an action, and you will grind it to be a spherical surface. And so it is easy to make spherical lenses. The problem with spherical lenses is that they don't have this property. They will not focus light to a point. The hyperbolic shape does. The sphere does for the innermost or so-called paraxial rays. See, they come to almost a point right there. But the rays that are out near the edges do not. They come to a different place. And that's just from the geometry of Snell's law and a circle. And this is called spherical aberration, the fact that they do not. And so you can actually go out and buy lenses that don't correct that aberration. And so an example is the Canon 135 soft focus lens. So it deliberately has spherical aberration that you can actually dial in and out. And so you can make this sort of gauzy, hazy look. So I say gauzy, hazy on purpose because it's a very specific effect. You can think of it as the convolution of an image with a function that looks sort of like this. Here's the convolution kernel. That's 1 over r squared. And so if you look at that convolution kernel, there's a spike in the middle. So it contains a sharply focused image, but then contributions of stuff that's further away from the middle. And that's what happens here. I actually did this digitally. I convolved this image with 1 over r squared. You have to do something special to get the sign right, of course, on that. Yeah, question?
So a lens like this was way more interesting before Photoshop?
Right, because I can do that with a convolution.
Yeah.
Exactly.
So do they still sell these?
Do they still sell these? I don't know. That's a good question. Yes, they do. Yes, they do.
Older lenses that are sought after for this.
Okay, so buy it now. It'll be $34,000 on eBay in a few years. So this is the convolution with that function. It's not an out-of-focus image. There's a sharp core and then contributions by stuff that's outside of it. You can simulate that by putting a silk stocking over the lens, and that's why I say this gauzy appearance. Okay, so you see that the slides turn orange. So to my Stanford students, this means they're not responsible for this material on exams. I'm going to go through this set of slides rather quickly. I'm not going to expect to bring all of you along. I just want you to kind of see the gestalt of what's happening here. I will then show a geometric construction that does the same thing, and I'll go through that more slowly, and it's a bit easier and more intuitive to understand. But I want you to see that you can do this whole thing algebraically if you'd like. So rather quickly, standard derivation of paraxial focusing. The assumption is that we're only dealing in the middle of the lens, a little bit of curvature, the rays that are nearly on the axis, and so that E is assumed to be very, very small. If E is very small, then a lot of things happen. So first of all, sorry, let me use the cursor here. The sine of U, for U in radians, which is the opposite over the hypotenuse, SOHCAHTOA, in elementary school, is, or in high school, is roughly equal to U, if U is represented in radians. So, what's that?
What is E in this picture?
Sorry, what E is the distance between the lens surface and a vertical drop. So as an example, get my numbers right. So the sine of 10 degrees equals 0.1736. 10 degrees in radians, which would be 10 degrees over 180 times pi equals 0.1745. So for small angles, the angle in radians is roughly equal to the sine. And so that is this approximation. So the cosine is roughly 1. So the cosine then is the adjacent over the hypotenuse. And then the tan will be then roughly equal to the sine, which will be roughly equal to the angle itself in radians. So this is called first order optics because if you take the Taylor series for sine and cosine and just take the first term, that sine of phi is phi for that first term. And the cosine of phi is 1. And then the rest of the terms refine that. So that's why it's called first order optics. And if you look at a plot, this is in degrees here. And here is the actual sine of phi and cosine and tangent of phi. You can see that the sine and the tangent are very close together until you get up to like 10 or 15, 20 degrees. Okay? Okay, so if you buy that, then we can re-represent, or we can approximate Snell's law by first re-representing it like this. So just multiply through and you get that. And then here's the paraxial approximation where we replace sine of I, there's the angle I, with just I. Okay? And n are the two refractive indices. And now we'll do a whole bunch of algebra that I'm not going to go through because it'd take too long. But the question we're trying to answer with this derivation is, given the object distance z, what is the image distance z prime? Where does this ray that's leaving a point on the axis come back to the axis? And so derivation, derivation, derivation. And what's interesting when you come up with this final formula is that h has canceled out. That's the key fact. So h is the height of this point of intersection. So if h cancels out, that means that every ray that leaves this, regardless of direction, will come back to the same point at the same z prime. That's called focusing. Right? So what happens in a special case where z, the object distance, is infinity, meaning it's all the way over there? Then you work through more algebra. You'll end up with z prime being this, which is defined as the focal length. We've already seen that geometrically. Question?
You had mentioned that in a lens you bend twice, once when you go in and once when you go
Right, and that's not being shown here. You'd have to...
The focal point is inside the glass observation?
I'll show that in just a second. Okay, so that's for air on the left and glass on the right. So here's exactly your question, which is what happens if you have two interfaces. So it's similar derivations. I'm not going to go through them here, but now I think you believe that you can just make these derivations. And so it bends twice, as I showed before. And here are the radii of the two circles, R1 and R2. And then as this distance between their two intersections, meaning the distance through which it transits in the glass, goes to 0, which is called the thin lens approximation, then we end up with this formula. There's the object distance, SO, which was Z before. Here's the image distance. The sensor is assumed to be over here. That's SI. And then there's this messy thing here. Okay. So hold on to your hats for just a minute longer. Then we'll break out and do a geometrical derivation. Starting from that same formula, and recalling that as the object distance goes out to infinity, the distance on the other side becomes f, the focal length. Then we can just replace this with this. Same right-hand side, equate the two left-hand sides, and you get this formula. That's called the Gaussian lens formula.
We also assumed index of refraction of air at 1, right?
Sorry?
Index of refraction of air at 1 is also an assumption in here?
Yes. Yes, because I've only got one index. Yes, sorry. Yeah, 1 right there. Yeah, sorry. Okay, so let's do the same thing now geometrically. So here's the Gauss's ray construction that I showed you before. And let's label a few things. On the left is the object distance, on the right is the image distance. Positive SO goes to the left, positive SI goes to the right by convention in diagrams like this. Positive Y is upward. That's just a convention that we'll use in the formulas. And now let's just start doing similar triangles. And so in similar triangles, we get that, so because this is negative, we have to take its absolute value. This is to this as the image distance is to the object distance. Okay, similar triangles. No sweat. There's the focal length, because that ray that's parallel to the axis does go through that point. And here are two other triangles. And now this says this is to this, which is the same as this, as this, which is SI minus F, is to F. That's this. Okay? So given those two, if you look at these formula now, you'll see that the left-hand sides are equal, so you can equate the right-hand sides and fiddle, and you get that. Same formula that we just derived before. So if you trust Gauss's ray construction, then you can get to the same formula using similar triangles. Question?
So in the geometric derivation, where is the paraxial approximation showing up? What in this picture corresponds?
Well, so the paraxial approximation is already true in the fact that you had to swallow the fact that parallel rays will go through this one point. Yeah. Which they don't for rays that are way non-paraxial. Okay, so I showed this slide last time. Let's go through it in a bit more detail now that we have this formula under our belt. To focus on objects at different distances, we move the sensor relative to the lens. And so here is how much we have to move that now, which we didn't have last time. Oh, flash demo time. So let's see. So here's one of the flash demos. It's linked into the website. And we can first move the object distance. And we see that the image distance moves commensurately. What's written here that you can't see because I had to crop it for this 800 by 600 screen is the Gaussian lens formula. Okay? So we can alternatively change the focal length of the lens. So that changes whether it's thick or thin and how much it bends the light. And so we have this nice animation of the piece of glass getting thicker. And so for a fixed object distance, it will focus closer. This is what a zoom lens does. Not really. The zoom lens doesn't actually make the glass thinner or thicker. We'll show how a practical one operates that has a combination of lenses that does effectively the same thing. But the fact that it changes the focal length like this is what a zoom lens does. Yeah.
Thin lens assumption in both cases, you're just changing the normals of the glass?
Yeah. Yeah. Exactly right. Okay, so we can do one other thing while we're here. Let's show the sensor size. So here's an assumed sensor, and those rays that go through the middle are showing you the field of view. And so you can see as I change the focal length, look what happens to the field of view. Wide angle lens, telephoto lens. And let me reset it. One more point I want to make, which is notice that these two are now at the same distance from the lens, and that that distance is twice the focal length. See that this distance is twice this distance. And if we go back to the slides, that's that case right there. The SO is equal to the SI is equal to twice the focal length. That's diagrammed here, and you can work that out from the Gaussian lens formula. It is true from the Gaussian lens formula. Okay, that's called one-to-one imaging, meaning that if a sensor is here and an object is here, an object will be reproduced at the same size because the field of view is the same on both sides. So that's a macro lens. We'll talk more about macro lenses. Okay, and one more case worth talking about is that you can't focus on objects that are closer than the focal length. You might not even be able to get that close, but you definitely can't get any closer than that, because these rays here would otherwise just not converge. There'd be no focus. So recap, geometrical optics, spherical lenses, thin lenses, and the paraxial approximation. Jumble them all together, do some derivations, and you get how camera lenses work. And it's the Gaussian lens formula. And we can, from it, determine the field of view, one-to-one imaging, and that minimum focus distance, which might be not even that short, depending on the mechanics of the lens, but certainly can't be any shorter than that. Any questions? Yes. Any burning questions? Sorry, I didn't mean to pick on you. I'm sure your question's burning. What's your question?
What I didn't understand was, so do we use hyperboloidal lenses in practice? Or?
No, we don't.
Okay.
No, we use spherical lenses. There are aspherical lenses, and they can reduce aberrations. But I don't think that those are hyperboloidal, because there are lots of other things you need to correct.
And is it just hard to machine a hyperboloidal?
You know, that's a good question. I'm not sure which aberrations they don't correct, and I don't know what that image looks like. Yeah, we'll talk about chromatic problems, and they won't correct those. In particular, we'll talk about that on Wednesday.
Overarching thing is that this is all for a single wavelength.
Right, yeah. And that's the chromatic aberration that I'll talk about on Wednesday. Florian.
Hyperboloid lenses are often used as condensers in the illumination part of projectors.
Used as the condensers in the illumination part of projectors. That's interesting. Okay. Because there they can be molded and you don't care so much about the chromatic aberration. Okay, so let's see if my Dory has anything interesting. No questions on the Dory. All right, we'll go on.
Sorry, can you just quickly remind me, so the focal length is proportional to the aperture number? Because it's wider, you can focus it more. It has nothing to do with that, it's just the shape of the lens. I'm trying to think, what attributes predict the focus distance of a lens?
It's just the shape of the lens and the index of refraction. Okay, so in fact, let's talk about different shaped lenses. So convex lenses are the ones we've been showing so far. Rays from infinity focus to a point at Fi. So if you have a concave lens, then the rays will actually diverge. Or if you plot them back, there'll be this point of convergence on the left side. And so there, what happened to my presenter display? Hold on one second. Technical problems here. Fascinating. I kind of need my presenter display, so you'll have to wait just 1 second while I fix this problem. It's apparently a yeah, so notes are there. Interesting. Huh. Okay, we're going to do this without notes. That's actually really surprising because the notes were there just a second ago. All right. So, oops. Right, so this is called a real image because you can actually put a piece of paper there and an image will appear. And so that's what a magnifying glass is. So a magnifying glass is a simple convex lens. And if I take one of those light sources, it will make a picture of the light source on here. That's called a real image. So a concave lens produces what's called a virtual image. So here's an example of each. So the focusing glass inside a camera makes this real image. Inside an SLR makes this real image. And so if I could remove the hump here, there would be underneath a little piece of diffuse glass. And this is what it looks like. It's focusing screen inside there. And it's making a real image there. If we remove the top of this, we could look at that image. But the concave lens doesn't do that. Concave lens, so here's an example of a concave lens. So if I look at something here, it only makes an image if I interpose another lens to bring those rays back together. That lens could be my eyes. It's or it could be a photograph that I take of this setup. But I need to do that, or it won't make an image out here. If I put a piece of paper here, nothing will happen. So, all right. So that's what's done up there in the focusing screen, which is right there. But on the right, I had to actually put another lens, like the photograph, the camera lens that took this picture of a concave lens. Okay, so let's talk about the power of a lens, because that's a simple way to compare the strength of different lenses. It's just 1 over the focal length. That's it. Reciprocal of focal length. It's in this scale called diopters. And so let's bring in an example. Here are my eyeglasses. They have the following prescription. Right eye is negative 0.75 diopters, so it's 1 over the focal length. And the right eye is negative 1 diopter. So what's wrong with me? What's that? Yeah, I'm slightly nearsighted, called myopia. And what it means is that if a perfect eye would focus light on the retina, my eyes focus here. And so I need a concave lens with negative power in order to stretch those, diverge those rays a bit before they reach the lens in my eye, and that'll bring them to a point there. Notice that if the rays were not coming from infinity, if they were coming from someplace closer, then from the Gaussian lens formula, they would focus a little bit further, and they might actually hit my retina without any correction. And that's why you see me taking off my glasses when I look at something that's close, because I don't need that correction for something that's close. So hyperopia is the opposite. That's farsightedness. And for that, you would use a convex lens instead of a concave lens. There's more wrong with me than that, but you'll find out that on Wednesday. Okay, so we can add diopters as a simple way of combining 2 lenses. So we can, if you work through some derivations that I'm not showing you, you can just say 1 over the reciprocal, you can just say the reciprocal sum of focal lengths makes the reciprocal of the total, or diopters, you just add them. And so an example would be if you were to put a 1 over 200, if you put a 200 millimeter lens in series with a 500 millimeter lens, you'd actually make this focal length, but it might be easier to just add the diopters. And so this notion of adding diopters is what leads to close-up filters, which you can buy for your camera. And so you screw it onto the end of the lens, and they are power designated in diopters. So there's a close-up filter that says +1 on it. So here's another one. Now, that one's not denoted in diopters. It instead gives the focal length, but just 1 over that is the number of diopters. So this is a more powerful close-up filter than this. And so the focal length of this one is 1 over 1 in meters, so that's focal length of 1 meter. And so this is a focal length of 500 millimeters. Stronger lens. Okay. So this, is, by the way, is not actually a single piece of glass. It's typically an achromat. We'll talk about that on Wednesday. It's actually multiple pieces of glass. So how might we use that? Let's take that and put it on one of the lenses that I have here. So I have a close-up filter, which is exactly that close-up filter you see there. And we'll screw it on the end, just like that. So now what is it doing? Changes the longest focal length from 200 millimeters to 143 millimeters, right? So it does exactly the formula that I just showed. And why would you use it? Because for a fixed image distance, it reduces the object distance. Lets you focus on something that's closer. So yeah, let's say at f200, so I'll change the, so there now the lens is set on f200. The lens minimum object distance is 1,000. So it can't focus on something as close as the as its focal distance, because this distance is just 250 millimeters, and that's just governed by the mechanics of this particular lens. That's the next formula, sorry. So its minimum object distance is 1,000, and its minimum object distance is 1,000. Its minimum image distance is 250, and that's what this is, 250. And so I can focus on something that is a meter away, but not any closer. I'll show you the images in a second. So I have to go a meter away. Suppose I would like to go closer. Okay, so with the close-up filter, I'll put the close-up filter back on. Now it becomes the minimum object distance becomes 334 instead of 1,000. So I can get 3x closer. So now I can come all the way up here and focus on that. Now if you think about the fields of view, if I'm back here with a fixed focal length lens, it's a 200, I'll get a certain field of view. That's going to be small in that field of view. If I can come up this much closer, that's going to be bigger. And so I can magnify more with a close-up filter because I can get closer to it without actually having a longer barrel on my camera. You see what close-up filters are for?
So what's the difference between doing that and just changing the zoom to 143?
It's because it allows me to effectively have a longer longer image distance. If I set it to 143, given the image distance that I really have, the object distance would still be fairly far. But this allows me to have a shorter object distance with the image distance that I am constrained to by the mechanics of the camera. Okay, so poor man's macro lens. I say poor man's because it's not well corrected for aberrations. It's not as good as having an actual macro lens. So to get ourselves comfortable with some of these concepts, let me define another term that's useful, which is the magnification. So the magnification, there's our usual suspects on the variables. The magnification is simply defined as this distance over that distance, or equivalently, this distance over this distance because of similar triangles. Okay? Negative here because of the funny way that y is negative here. And so if we go back to this case and look at the magnifications, this is -1 to 4, 1/4. It's often written in photography like this. And the magnification of this one is 3 to 4, closer to 1-to-1 imaging. In other words, an object almost gets as big on the sensor as it was there. It's my effective object distance. Sorry, this is 250, this is 334. That's almost 1-to-1. Not quite 1-to-1. Okay. Switch gears. So lenses are not thin, they're actually thick, and there are a couple of properties that we ought to consider. We're not going to go through all of this, that's why it's an orange tinted slide. But there's one point on all this stuff that is important for you as a photographer to understand, and that's the center of perspective. So the way to think about it is, in a thin lens, the chief ray from a point is that ray that traverses the lens through its optical center without changing direction. So here's a chief ray. There are chief rays of many different angles. They do shift a little bit in a thick lens, but they don't change their direction because of the way Snell's law works. So in a thick lens, the intersections of this ray with the optical axes are called the nodal points. For lens and air, these coincide with the principal points. Don't worry about these definitions. All you care about is that first nodal point, which is called the center of perspective. Because if you think about it, all the rays seem to come together to that. So you remember the way I defined perspective at the very beginning of the course. If I hold out my finger, I can draw a line between you and my finger and my eye, and then I, without moving, do the same thing over here, and those rays will converge to a point, and that's the center of perspective. That is the first principal point, or first nodal point for a lens in air. And so if we were going to rotate the camera for a panorama and want to get a perfect panorama, we should rotate around that point. Where that point is depends on the design of the lens. All right, here's another interesting fact about lenses. They make a 3D transformation in space. So as a graphics person, I think this is just so cool. And let's see, maybe what I'll do is I'll show the applet first. Let's do that. So there's a nice applet that goes along with this. So we're making just real images. There's the real image. And let me switch to the applet. Right. Okay, so this is just the Gaussian lens formula, but I've got a slightly different way of manipulating it. So we can look at Gauss's construction. So you see how as I go down here, I've got a ray that is parallel to the axis. I've got a ray that goes through the middle, and it shows where it will focus on the sensor. Here we are at an object space. Now watch what happens when I go away from the lens. Look at that. Isn't that a weird effect? I'm going parallel to the optical axis, but that's not what Gauss's ray construction is saying on the other side. I'm just following Snell's law. So one way to draw that is we can say there's a three-dimensional space on this side, and let me just draw these arrows in order to, and then we have a lens. And then if you plot every single point here and what it ends up here, you produce a shape that looks like this. So what is this shape called? Well, it's a truncated pyramid. It's a special name for it. Frustum. Yeah. So in computer graphics and OpenGL, we know about these frustra because they're sometimes frustrating because you can't figure out where to put. Oops, sorry. So that's going to be reversed, right? And let's see. 1 will end up over here. 2 will end up over here. And now all a sensor does is it makes a slice of that. In other words, the lens transforms a three-dimensional space, a three-dimensional rectilinear space into this frustum space, and then there's an intersection here, which is what the lens does. It pulls a slice out of that. So so there are a number of implications of this. Let me go back to the slides. Oops. So one implication of this is that as an object moves linearly in Z, so here you can see linear motions over here, the image moves non-proportionally in Z prime. So another implication is if you move a lens linearly with respect to the sensor, that would be linear motions here, it would be non-proportional over here. And so if you look at any lenses focusing, so here's a lens with manual focus, it's my Leica lens, the focusing positions are not evenly spaced. So this is a screw motion. That's doing a linear motion. You know, if I do a quarter of a turn here, it's moving it out a certain amount. If I do another quarter of a turn here, it's moving a certain amount. So the lens motion is linear, but the points in the scene on which it's focusing change non-linearly. That's exactly due to that, which is exactly due to this, and you can work it out from Snell's law. And another effect is that apparently, so if I were to move the sensor to a different place, I'll be focusing on different points that are here. It also changes size. It appears to get bigger. That's actually true. And so if you take a manual focus lens, or if you watch any lens focus, it seems to breathe a little bit. Actually is this effect here. It's not a big change, but there's a small change in scale that happens because of this effect when you focus a lens. Videographers will call that a lens that's breathing. Okay, so more implications of the Gaussian lens formula. We've talked about convex, concave. We've talked about power, combining lenses, close-up filters, and then this idea of the 3D transformation. So I know there's been a lot of material here. Any questions here? It's a good time to kind of stop and take a breather for a second. Yeah.
The significance of the second focal, point, the second nodal point.
Oh, you mean not the first nodal point, but the other nodal points. I would have to look it up to find something intuitive to tell you about why those are important. Certainly they're going to be important as to where you put the aperture and what the effective aperture is going to be, because the aperture is going to be governed. What the real aperture is going to be governed by where those other nodal points are and where those rays begin to diverge. That's just off the top of my head. There are probably other effects as well. Yeah.
Is the first nodal point marked on the lens?
Wouldn't that be nice? No. And one of the reasons is it probably moves around, depending on whether it's a zoom or a focusable lens.
For common lenses, people have worked them out. You can find them online.
You find the locations of those nodal points and therefore the point of perspective. You can calibrate a lens. You can effectively do an experiment like that and figure out where it is for a lens just by tracing those rays back. In computer vision, we can just put calibration objects at multiple distances and work that out. Yeah.
You had mentioned the close-up filter as sort of a poor person's macro lens. Is that basically how a macro lens works? Just more integrated, or?
I will talk about a macro lens shortly, like in 5 minutes.
Are we supposed to understand by now why the lenses have so many pieces of glass? Or just
No.
Okay.
No, we'll talk about.
Sure, I could follow from
No, that's right. That's right. So far, we're still doing thin lens approximations. On Wednesday, we'll talk about aberrations, and as we correct them, we'll begin to add more lenses. I won't explain all 23 pieces of glass in that lens at the beginning, but we will begin to understand why there are more pieces of glass. Okay, well,
Question.
yeah.
Is there any use for the nodal point before people started shooting panos?
Is there any use for the nodal point before people started shooting panos?
Center of
Oh, yeah, the center of perspective. That's a good question.
I was just thinking about it, because I mean, you would expect somebody would have started at least publishing information, like Leica publishes all sorts of other information about their lenses. I don't think they published that one.
Well, see, it's certainly important if you want to think about vignetting. Then you need to know where those rays are. But vignetting is mostly important to the photographic designer as they design the lens hoods, for example.
Yeah.
So, Florian.
Computer graphics is one, merging computer graphics and real imagery is one use for it.
Right. Yeah, so merging computer graphics and real imagery, you would need to have a calibration for the camera, including knowing where the point of perspective is. Okay, let me check the Dory and then we'll go on. Oh, okay. Whenever there's a live question, could you repeat the question so that people on the live stream, I'm trying to do that. I will try harder. Do cameras which are marketed for underwater photography have different lenses to account for the different refractive index? That's a great question. So I'm not an underwater photographer, but it's fairly obvious that there'll be a difference of index, glass versus water versus glass versus air. So one way you can solve that is by making sure that it is glass versus air and that there's another piece of glass out there, which is the air-water boundary, and that one's flat. And there's an animal that does that, actually. The animal that has to live in both sea and land, a seal. And so they actually have an optical arrangement like that so that they can focus effectively in both water and air. That's one solution. You can imagine other solutions, but that is an easy solution. It's just make sure that the boundary to the water is flat. So how do close-up filters compare with extension tubes? 5 minutes, you'll see. What materials is the focusing screen made of? I have no idea. Plastic. And it's a little Fresnel lens. It's got a bunch of little bumps in it, which are capturing the image so that it appears on there. That's about all I know about that. Wow, these are questions I do not get in at Stanford. All right, let's keep going. So let's now talk about depth of field. So this much I said last week. It goes as the F number. But let's go into it in a little bit more detail. So first of all, lower N means a wider aperture and less depth of field. Another orange slide. If you consider the thick lens and very large apertures, it's actually not exactly just that distance. You can think of the refraction as taking place in this thing called an equivalent refracting surface, which is actually a spherical surface inside the thick lens. And that, as that begins to curve here, it begins to become meaningless to talk about refraction. It won't come to a focus at a point anymore. And so you have to replace this thing, and the lowest possible N in air is 0.5. And that's the point at which this actually gets up. Whoops, sorry. This actually gets up to 90 degrees up here. So that's the theoretical maximum. You can't actually achieve that. The lowest N I've ever seen in a single lens reflex camera is f1. There's a Leica lens that's 0.95. And Stanley Kubrick in Barry Lyndon, who wanted to do his cinematography by candlelight only, borrowed a lens from NASA that is 0.7. I can't imagine how much this thing cost. And he was able to make a movie partially by candlelight. I think there's audio on this. This is the seduction scene. And it's shot just by candlelight. Very shallow depth of field. Very shallow depth of field because of the low F number. Okay, so let's refresh our memory of the meaning of the depth of field. If you've got an object plane focused to a film or sensor plane, and you want to ask what about points that are a little bit closer to the lens, so they'll, because of the Gaussian lens formula, focus back here. When they encounter the sensor plane, they have not yet converged. They'll make a little disk. And the question is that disk too big for you or not too big for you? Do you call it out of focus or do you call it not out of focus? That's the permissible circle of confusion. Or if the point is too far away from the lens, it'll do the same thing. It'll cross here and make a circle on the sensor. And depending on what you call your permissible circle of confusion, you'll get a depth of field out here. So that's the intuition for it. What that permissible circle of confusion C is depends on a lot of stuff. It depends on the sensing medium, the reproduction medium, the viewing distance, human vision, because effectively we're saying how big an angular subtense on your retina do you consider to be a spot versus a blob. So we'll work out some exact examples a little bit later in the course when we talk about sensors and sensor sizes. But for print from 35 millimeter film, it's often said that 0.02 millimeters is which is 20 microns, is the allowable circle of confusion on the negative, on a 24 by 36 negative. For high-end single lens reflex cameras, it's often said that 1 pixel should be the allowable circle of confusion. And that might be maybe 6 microns, maybe it's getting a bit smaller now. If you're downsizing it or you're displaying it here on this projector which has a low resolution, then you can get by with a larger circle of confusion. Okay, so we'll talk about that and tie it to visual angle a little bit later in the course. So here's a construction that will help you think about depth of field. So here is that allowable circle of confusion on the sensor, and points that came together here or here will, at the sensor, not be any larger than that circle of confusion. So the points can be anywhere between here, and they will call them in focus. So we'll shade that little area. The conjugate of that area out here, so the conjugate means just what happens on the other side of the lens, is that. Okay? So the first thing to notice, depth of field, depth of focus. The first thing to notice is that it's asymmetrical around the in-focus image plane, object plane. Remember I said that? That was one of the mistakes, not mistakes, one of the approximations that London makes in his textbook. There's more stuff in focus further from the lens than there is closer to the lens, and that just is another property of the Gaussian lens formula when applied to this problem. Okay, so let's define that as C, the circle of confusion, and there's how big that is in object space, where MT, if you remember, is the transverse magnification. So that just says how big that circle of confusion is out in the world. And now let's do some similar triangles again. It's typically, let's see, it's typically larger than C, because what goes on out in the real world is typically bigger than what's happening inside your camera. Okay, similar triangles, lots of similar triangles. We need F, the focal length, and we need U, which by convention in depth of field formulas is our object distance. It's SO in the previous slides, but I'm going to use the convention for each formula. So that's roughly equal to the circle of confusion times the ratio of those two, roughly. And then if it is, then we can do this similar triangle. There's the aperture, A equals F over N, the aperture diameter. There's the first distance we'd like to compute. We'd like to know how far in front of the in-focus plane stuff would still be in focus according to our allowable circle of confusion. And there's the formula. And all that is similar triangles between D1 is to that height, which is there, as this distance, U minus D1, is to the aperture height, which is F over N. Okay, similar triangles. Dot, 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 a bunch of algebraic derivations come out with that formula. You can do the same thing for the far half of it, because it is asymmetrical, and you get that. Okay, so those are the two formulas. And here they are again. I just added them together. Now, you can ignore some of these terms for typical practical cameras if the conjugate of the circle of confusion is small relative to the aperture, meaning my circle of confusion out in object space is going to be some millimeter size feature or 2 millimeter size feature that is the largest I will allow. That's typically smaller than the aperture when we're talking about depths of fields of big lenses. The aperture is several centimeters. So under that assumption, a little bit of hand waving, we get a simpler formula because some of the terms drop out. That's the formula that we'll use here. It's a very simple formula. It's the same one I put up first day of class. The F number of the lens, the size of the circle of confusion in the image plane, so microns or pixels, the distance to the in-focus plane in object space, roughly from the lens, or from the camera, and the focal length of the lens. Okay, let's play with this formula a little bit. So here's a picture I took in India, and there's the formula. So that's an EXF1. I don't have that. It's an old camera. Don't have that camera with me. But it was f4.1. It had 2.5 micron pixels. The distance to her was 19 feet. And I was using a 73 millimeter lens. Now that's on a crop factor camera. And so if you want to think about how telephoto was that, it was 362. So it's really a telephoto shot. But the number 73, is the number that we use in the formula. And if we just plug and play, that comes out to a depth of field from the frontmost to the backmost thing that would be in focus of 132 millimeters. Okay. Now, you're not experiencing the same thing yourself right here because one pixel on this video projector, I don't know how Spielberg's encoding it, but maybe it's also 800 by 600, is effectively a larger circle of confusion. And so if we multiply by that, the depth of field will be 464 millimeters. So that's roughly like that. It's about half a meter. There. So that's certainly enough to incorporate anyone's head at that distance. So her head is fully in focus in this scene. Okay, let's run another example. So this is the Sun Temple at Karnak. Konark, sorry. And there are the numbers there. So the distance to these guys is about 56 feet. I'm using a much wider angle lens, 27, which is the equivalent of 135, and the depth of field is 41 feet. So that's not enough to include the background. It's a bit hazy, but it's also not quite in focus. It's probably closer to being in focus for you guys because the depth of field effective on this projector is 145 feet. But when I look at the original picture, the temple's not in focus. Come back and talk about how I could have fixed that in a moment. A couple of other examples. Close-ups. This is an SLR, so I've got a large circle of confusion. I've got large pixels, very close. Depth of field is pretty small, a little bit larger, 11 millimeters, but you can easily see things that are out of focus here. Okay, let's get even more extreme. Here's a macro lens, the Canon 65 millimeter macro lens. And so it's a 5-to-1 macro. That means that things are going to be 5 times larger on the sensor than they are in the real world. What can you look at that you want to see that big? Well, mostly bugs. Well, maybe you don't want to look at bugs, but so here are the numbers for that. Now you have to be a little bit careful when you're talking about short conjugates, meaning stuff that's really close to the lens. And if you go to an optics textbook, unfortunately not a photography book, you'll find a change to n prime. So n prime is f16. And if you plug that into the formula, you'll get 0.29 millimeters as the depth of field. And well, I don't know this guy intimately, but you can certainly see that even parts of his head are out of focus. So let me take a little side light here on macro lenses. So something should be kind of confusing you already. I call that the MP is a 65 millimeter macro lens, and the Casio EXF1 was at 73 millimeters, almost the same focal length. But one was a macro lens and one was not a macro lens. So what's with that? And the answer is that they are built to have much different image distances and therefore object distances. So if we just apply the Gaussian lens formula, a normal lens will have a small image distance and a long object distance. Now these are just snapshots out of my applet. But the macro lens is built to have a very long object distance. And in fact, if you look at this lens, there's the first glass element out here. There's the camera over here. That's a pretty long distance. This is an amazing mechanical construction in there.
Probably mention that your subject stays approximately 4 inches off the front of the lens no matter what.
Not on this one. I think it's a lot closer.
Yeah,
It's a lot closer.
No matter where you have that tube swung out, the thing you're actually taking pictures
Right.
of is right close to
Yeah, so what Zalman's pointing out is that this is actually changing the focal length and therefore the magnification. It's not changing the focus distance. It actually has no focusing lens. You focus by doing this. So this changes SO, which changes the magnification. And this is actually, this says 1-to-1 up to 5-to-1. Most macro lenses are 1 to 5. And so there are the sensor sizes that can make you understand. So it's a small sensor, large object typically, but a large sensor and the same or even smaller object. Macro lenses are also well corrected for aberrations at those short object distances. And we'll talk about that next week. And so that's why it's worth getting a macro lens. But if you don't happen to have $1,500 for that lens, you can instead get an extension tube. So extension tubes, and here is one, is just something that goes in here, in between the camera and your lens, and takes your lens and moves it out a little bit. It's got no optics in it. See? It's just a tube, although it does transmit the electronics through there. It's a little bit more complicated than that. So because it has no optics in it, you can build one from a toilet paper tube, as a student did in my class in 2009, who is now a SWE at Google, Katie Dektar. And she could take pictures of her carpet. Because what it does, if you move the SI out, it makes the SO shorter. And so you can get close to stuff. And if you get close to stuff, as I showed with the close-up filter, you magnify it more.
Give the light more time to converge before it hits the center.
More time, well, I mean, more distance, yeah. Right. So let's compare these two, extension tubes versus close-up filters. Both allow closer focusing, hence greater magnification. Both degrade the image quality relative to a well-corrected lens for those situations. Extension tubes work best with wide-angle lenses, and close-up filters work best with telephoto lenses, just because of the way the image quality performance will end up working. And the extension tubes, because they take the aperture of the camera and move it a little bit further away, will reduce the effective F number. You think of the F number as the diameter of the aperture in here over that focal length. And if we keep the diameter the same and move the thing out, because we've got a tube in the middle, then it's going to increase the F number, reduce the effective aperture. You only need one extension tube, though, whereas you would need a different close-up filter for every lens filter diameter, because you have to screw it onto the end of the lens. While we're at it, let's go a little bit further tangential and add one more thing that people think of at the same time, which is teleconverters. So let's get them all three up there at the same time. So a teleconverter looks kind of like an extension tube, except that it does have optics in there, so I can't stick my finger through it. And you put that in the same place, typically with a telephoto lens. So you'll stick it right here, nicely color coordinated, and then put the camera. And so what it does, let me cover that again because it does have optics in it. So what it does, it increases the focal length, narrowing the field of view and increasing magnification, but it doesn't change the focusing range. So if you suddenly need, if that grizzly bear is about as close as you want it to be, but you'd like it to fill the frame, then you'll put a teleconverter on the end. They raise the F number as well because they're taking your main aperture and sticking it further from your camera. And they're awkward to add or remove, especially if there's a grizzly bear out there. Okay, so there's a nice comparison of all this stuff at that website. All right, let's get back to business here. Yeah.
What about reverse lenses?
Reverse.
Reverse lenses, taking a second lens and putting it on the end of the...
Similar to the
Yeah, so I think what Peter is saying is that you can take a male-to-male adapter, put it on the end of any lens, and then put another lens on the outside of that. And you can make weird combinations of relay lenses by doing that.
also bellows. I mean, people get seriously into macro photography have tons of techniques.
Right, right. Okay.
Straight to the camera body by just reversing it.
Well, right, yeah, you can take that male-to-male and then attach it directly to the camera body. That's right, yes. The electronics have to do some pretty strange stuff where you need a cable or something like that.
Manually focus it up.
Right, yes, yeah, I forgot that use of a reversing adapter. Yeah, you can do all kinds of strange stuff. All right, so we only have a couple more minutes. Let's go a little bit into that. So that formula goes linearly with the F number. And so you can do little experiments like that with different F numbers and see more stuff gets into focus. So there is a flash demo that you can play with. Let me actually show one more slide before I show the flash demo. It goes as the square of the distance to the object. And so you can see that if I go further from the object, stuff gets more in focus. And so there's a flash demo. There. Here's a depth of field demo. And you can play with this demo. You'll have a lot of fun. You play with the F number. There's the formula right there. You can play with the focus distance. You can play with the object distance. So there are two things here. One is that formula, which is approximate, and the other is a ray trace that actually is computing the size of these areas according to the correct geometry. So here's a fun. We change, let's change the F number. 0.5 is an unreasonable F number, but it's done so that this applet doesn't look ridiculous. But let's change it to a more reasonable one like 1.2. And let's take the subject distance way out. And the ray trace at some point will show infinity, meaning these rays never converge. They're at infinity. That means that everything from here to infinity is in focus. That is called, this magical distance at which that happens is called the hyperfocal distance. And I think we're out of time, so what I'll do is I'll give the derivation for the hyperfocal distance, and I'll show you some of the things it's good for next time. So let's stop there.